All right, so I posted an announcement this morning. I don't take late work in general, but there are a few cases where people have talked to me about extenuating circumstances and have asked to turn something in a little bit late and so on. So Friday at noon is my last deadline. Okay, other than the final exam, your grades are locked in as of Friday at noon. So go through Canvas, go through your memory, whatever it takes. And if there's something that, you know, I submitted ODP 402 and I got 10 out of 10, but it says 0, right? Before Friday at noon, please. Okay, otherwise during exam week while I'm trying to grade, I got to start juggling all these things and going back through history and stuff like that, and it's not practical. So the craziness starts this weekend basically. So if you can make sure you got everything that you feel you should get through Canvas and so on, and talk to me about it before then if possible, that would be great. And if you didn't bring in your extra credit signature sheet, bring it in tomorrow, okay? And get your points for that. So so any questions up through here? Other comments on the presentation, anything like that? Yeah?
I think we have less people than last year. Do we?
Less people?
Yeah.
Well, it depends what time you're looking at. A lot of people left early. So if you stayed all the way to the end, thank you for staying all the way to the end. But probably about half the people left after an hour.
I can stay from very beginning to end.
Yeah?
I remember last year that even the whole was so long filled up with groups.
Yeah. So every time that we do this, it comes out a little different. And this was the first time I've seen it done like this. It was almost done like kind of an informal mixer. So a lot of people were walking around holding their posters, and they'd go over to someone and talk to them and say, what are you doing? And they'd tell them, and they'd hand them their signature, and then they'd hand the other person their signature, and they'd say, what are you doing? And they'd tell them, and then they'd go off in different directions. And that almost kind of makes sense for a fall version of this, because you don't usually have, you know, a table full of stuff that you know, a laptop and things you've made and so on. It's really kind of a meet and greet sort of scenario. So I'm not sure I don't like that. I got to think about it. But a few consequences of that. One was that people got their signatures done after about 20 minutes in some cases. And some people thought that that was the goal, right? Which it's not. The goal is to be there for 2 hours, really. But I also wonder if maybe people walking by looked in, saw all these people inside, and decided not to go in because it looked crowded. Whereas in the past, we sort of had tables, you know, in the room, in the hallway and stuff where people were sitting. And then it's kind of more welcoming to somebody who's just walking by saying like, oh, here's a room full of people ready to talk to me. And you can go through and visit the different stations and see what they're doing and talk to them if you want. And so it was interesting. We'll definitely make some changes in winter quarter. I'm going to try to get people to sit down and have people come over and talk with you. So we'll see how that works. But I thought it was cool. I saw a lot of cool projects. I read everybody's original proposal, and I looked at your posters when you uploaded them. But it's still really cool to actually like talk to people and kind of see where they're at and hear their visions for where this work is going. So I thought that was pretty cool. All right, well, did we start at all talking about structures yesterday? Okay, so tomorrow and Friday I want to leave for reviewing and talking about the exam and so on and so forth. So today I want to just kind of like give you a little bit of a heads up on kind of where we're going in winter. So this is not stuff that's going to be on the final exam, right? This is just sort of a preview to kind of get your brains going in that direction. So when we did PA4, we were making a dictionary. So we had a two-dimensional array for storing 1,000 phrases of 201 characters. And we had an array of counts. So an integer array that told us how many times each phrase occurred. And the way we set this up was that if you looked at, say, dictionary bracket I, that's a character star. Okay, it's an array of 201 characters. It's a string. So this is whatever the ith phrase is in your dictionary. And count would be number of times this phrase appeared. And so the term for this kind of setup is sometimes parallel arrays. Two arrays, but the ith entry in this array corresponds somehow to the ith entry in that array, right? If you want to know how many times this phrase occurred, it's that location in the corresponding count array. And we could envision more of these. We might have implemented an array of integers called first, with the understanding that first I is the location of the first time this phrase occurs. So maybe for some reason you wanted to know not just what the phrases were and how many times they occurred, but where was the first time that phrase occurred? Was it in the beginning of the input or in the middle or the end and so on? So we might store the location where that phrase occurs. And so we have another parallel array. And parallel arrays work fine, except that, one, it's a lot of stuff to juggle. If I wanted to print my dictionary with a print routine, I'd have to pass it my dictionary array, my count array, and my first array. So you got to manipulate all these things. And when you're sorting, remember, if you're sorting your dictionary by phrase length, we do a bubble sort, we swap entries. Every time you swap a pair of entries here, you also have to swap the corresponding entries in the count array and the corresponding entries in the first array. You have to treat them all as a single unit, right? And then we also have this integer that tells us how big our dictionary is, so number of entries. And if num entries is 10, then dictionary count and first each have 10 elements in them, right? So all this information has to get kind of carried around together, and that's inconvenient. So one of the main themes in 222 is to work with what are called structures. So C supports a structure statement. I'm pretty sure you touch on this in 121. And it basically is just a way that the language supports taking a collection of things like this and treating them as one logical entity. So a typical structure statement, keyword struct, and then whatever you want to call your structure. It's like a new data type, basically. So, I don't know. We'll make a structure called dictionary. And then you go ahead and you just define all of your pieces of what a dictionary contains. So it's got a two-dimensional character array named dict. It's got an array of 1,000 integers called count first. It's got an integer that's a number of entries. Close that off, put a semicolon at the end. And now we've basically defined a new type of variable. So we have integers, we have characters, we have doubles. We have a new type of variable, which is called a struct dictionary. And if I say struct dictionary D, D is all of this stuff. Okay, so let's make this a little more usable because we've got a structure, but we've still got these parallel arrays inside. So let's take a step back. And let's make a struct dictionary entry. So this is going to be one entry in our dictionary. And we're going to need the following things. We're going to need to store the phrase. So that's going to be a string of 200 characters. we're going to want to store how many times that phrase occurred. That's our count. I'm just making it a little more interesting by adding this other variable where we store the first time the phrase occurs. So that's an integer first. And so this represents one piece of our dictionary, but it's got all three of these components: the phrase, the occurrence count, the location where it first appeared. And now I can say struct dictionary entry, I don't know, DE. And DE is a new type of variable that has all of these three pieces in it. And so I can say something like DE period count equals 0. So DE is a structure, count first phrase, we call these things fields. Okay, so this is the count field of this structure DE, and we're saying set that equal to 0. DE.count is an integer. We can do anything that we can do with an integer. So we can initialize it, we can increment it, and so on and so forth. DE.phrase is a character array of 201 elements. It's a string. We can do anything with it that we could do with a string. For example, we could say, let's find the string length of DE.phrase. That's perfectly valid. But if we want to print an entry from our dictionary, right, we could just say print, and we could pass it our dictionary entry. And our function print, that we're going to write later maybe, since we're passing it a dictionary entry, it can get to the phrase and the count in the first by saying whatever its argument is, .phrase, .count, .first, right? So this is all somewhat familiar, right? Okay. So if we want an actual dictionary, we can do this. You can say struct dictionary entry, dictionary bracket 1000, and now dictionary is an array of 1,000 entries. And if we say dictionary bracket I, that's one entry in our dictionary, it's the ith entry. And we can say dictionary I dot phrase or dot count or whatever. So it kind of like hides the complexity that we need all these different pieces for a dictionary entry, right, until we actually need to deal with them. So somewhere we might have to actually deal with those individual pieces, but for building them in an array, for sorting them, for moving them around from function to function, it's really just a single variable, right, that happens to be kind of a super variable. But if we want to sort, right, we can swap two entries in this dictionary array, and when we swap those entries, we're swapping the phrases and the counts and the firsts and everything else, right? So it's a convenience. It makes your code a little cleaner, but it really moves us in a direction that we're heading to in Spring, which is dealing with objects, working with an object-oriented paradigm. So what we've done here is taken some things that logically belong together and grouped them into a single thing. But all those things that we grouped together were pieces of data. If we take this one step further, we can also start lumping in pieces of code. So we can say, you know, when I have a dictionary entry, sometimes I want to print that. And when I print it, what I want to do is print out an angle bracket and then a 5-digit number that comes from the count, a closing angle bracket, and then I want to print out the phrase and I want a new line at the end, right? And that's how we're going to print a dictionary entry for PA4. And really that print routine only makes sense when we're dealing with a dictionary entry, right? Because that print routine is supposed to print a count and then a phrase, and it doesn't make sense to pass, you know, some random variable to this. So that print function really is part of this structure. And in an object-oriented paradigm, we could have this dictionary entry that contains these pieces of data, but would also contain that print function. And then if we wanted to print dictionary entry, we could actually say dictionary entry.print. Just like we can say dictionary entry.phrase, dictionary entry.length.count, we can say dictionary entry dot the name of a function. And if that function is part of the structure, it goes ahead and runs that function. And once we got that, then we're in an object-oriented world. And then life gets really good, because we can take things that make sense and that really belong together, and we can bundle them into these things that'll be called objects, and we can just sling objects around wherever we want, and we get a hold of an object that's got all these functions that go along with the data. And it's a different mindset, but it becomes a really natural way to think about things. And Java, which is what we'll be studying object-oriented programming with, is just ridiculously fun and easy to program in. Because all the low-level stuff that we've been doing in here and that we're going to do in 222 has been done for you in Java. Right? We're going to spend next quarter learning about things like linked lists and binary search trees and hashes and things like that, and we're going to write code from the ground up for implementing these different kinds of data structures. But in Java, these things, they're already there for us, right? And if we want a linked list, we can just say, give me a linked list called, X. And if we want to print out the contents of that linked list, we can say x.print. And if we want to insert something, we can say x.insert and tell it what we want to insert, right? So we'll be building up these things in 222 in winter, but then we'll start using them from this pre-existing realm in Java in 223. All right, so that's where we're heading. But 222, we're not doing objects yet. We're just doing structures. So one of the nice things about structures, as I said, is you can pass them around. All right, so got our structure. So we'll make a structure dictionary entry, and I'll just call it DE. And we'll just play around with setting the values in some of these fields, so we'll set those fields accordingly. And then let's see what we got. All right, so basic test code here. Just defining a structure, loading up some values in the fields, and then we're just going to print out those fields and make sure the universe still works. And it looks like the universe still works. Okay, so that's good. So here's something else we can do. Let's make a function. let's make a print routine. And let's just pass our dictionary entry to this print routine. So we'll write a print function that takes a dict entry, we'll call it arg, and we'll just do our print routine in our print call in this function. And this does exactly the same thing, right? But it's modularized. But to print this dictionary entry, which has 3 pieces of information in it, we only had to pass one thing to the print function, which was just the name of our structure variable. So far, that's good. So let's go in our main program and let's look at our dictionary entry before we make this call. Let's go ahead and do our call, and then let's look at it after the call. And in our dictionary, in our print routine, let's go ahead and make some changes. So inside our print routine, we'll go ahead and we'll print out the arguments that we got, which should be the same as what was passed. And then we'll go ahead and we'll make some changes to the fields, and we'll print those out and confirm that those changes took. And so before we called, count was 17, our phrase was hello. When we got inside print, count and phrase were exactly the same. We changed those fields, we printed out the new value of arg, and those fields had changed. And when we got back to main, they reverted back to their old value, which is a little sad. But it's not unexpected. Or is it? So we called our print routine, we passed it our structure, and down here we clearly took the fields of those structures, that structure, and we changed those fields, and we printed them out and confirmed that they were changed, and when we got back up here they were back to their old value. Why is that? Because it's not a pointer. Right, so the only buzz phrase you got to remember, pass by value. So remember, I mean, we've done this before. So our main program has an integer I, we pass it to a function, then we print out the value of I. And in our function, we set I to 12 and we return. And when we come up here and we print I, it prints out a 0. Right? And the reason for that is when we call function I, we're really saying function 0, because that's the value of I at that point. Okay, that's what pass by value means. It means take the value of the argument, pass that to the function. So we're really calling function of 0. So when we come down here, function I, this says set I equal to 0. This says set I equal to 12. This says return. But we haven't done anything with this. Right? And if I call this function argument x, then when we get into this function that says set x equal to 0, this says set x equal to 12, and then return, And clearly it's got nothing to do with this variable. Right? It doesn't have the same name. Names are meaningless anyway. But we're changing a local variable. So how do we fix this in this case if we want to actually have our function change the value of this variable? What's the trick we do? Pass a pointer. So pass the address of I and tell it that x is a pointer to an integer, and then say take the thing pointed to by x and set that equal to 12. Right? And we're still passing by value. This is now saying function of, some memory location. And so when we come in here, it says x equals that same number. But we're not changing x. We're saying take the thing that x points to, which is where I is stored up here, set that equal to 12. Okay, so we can do the same thing with structures. So let's pass the address of D. Let's prototype our function to say it expects a pointer to a dictionary entry. And then inside here, let's tell it that arg is a pointer to a dictionary entry. I'm going to get brave here. I'm sure I broke something, but we'll see. So I changed all my args to be the thing pointed to by arg, which should be a dictionary, and I'll pick off the fields from that. Hey, it compiles. Must be right. All right, so this is what we wanted to have happen. Before we called, count was 17, phrase was hello. When we got inside our function, those were the same values for count and phrase. We modified them, and inside our function we confirmed that they had their modified value, but when we got back to main and we printed out the fields, they were still the modified values. All right? And that's because we didn't pass a copy of the structure. We actually passed the location in memory where the structure is. And this business over here, star arg dot, all right, says arg is a pointer. It tells us where the structure is. So go to that location. So star arg is the original structure. Pick off the count field, for example, and set that equal to 1,111. So does that mostly make sense? So we're going to write things like this fairly often. Structure something, dictionary entry as a pointer. And we're going to write star de dot field. Well, let me show you a slightly unpleasant structure. Alright, so here's a structure called fun, and the interesting part of it is it contains a pointer to a structure called more. And more is a structure that contains, I don't know, A, B, and C. So we're storing vectors or something in there. And we have struct fun, and we have a pointer to that called my variable. All right, so here's the setup. My variable is pointing to a structure fun. Structure fun contains a pointer to a structure more. Structure more contains fields A, B, and C. Suppose I want to get to this A, B, C, these variables, inside the thing pointed to by my var. So the normal way we would unroll this is we would take my var, we would take the thing pointed to by that, and then we want to look at the ha field, so we would say dot ha, and since that's a pointer to a structure more, we're going to take the thing that that points to. So this thing is a structure more now, and we could pick off the C field, for example. And this is not something you want to spend 10 weeks writing.
How would you write that with an arrow?
So we're going to use a different notation for this. So when we say thing pointed to by DE dot field, we have a shorthand for that, which is just DE arrow field. So this is valid C syntax, and it's a shorthand basically saying take the thing that DE points to, that's a structure that should have a field with this name, give me that field. And the main advantage of doing this is that we don't have to write things like this, because this would become the following. My variable is a pointer, so take the thing it points to, which is a struct fun, and give me the ha field. And ha is itself a pointer, so take the thing that that points to and give me the C field. And so we've got my variable points to ha, points to C.
How about A and B?
Or A or B. All right, so if you don't use the arrow notation, you can still do what you want to do with this kind of thing, but that'll drive you nuts. Okay, that looks like a language called Lisp. And this will just make a whole lot more sense. And the kinds of things we're going to be doing in 222, the structures we're going to be building up, are all going to be based on pointers. So we're always going to be dereferencing pointers, but the arrow looks like it's pointing to something, which is what it really is doing. So it'll make things a whole lot smoother. Here's the other advantage of pointers. We can do things like this, bless you, and it's perfectly legal. We can define a structure called node that has two fields. The first is an integer called data. The second is a field called next, and it points to another struct node. And this is not really recursive. Now this would be a problem. Right, this we can't write, because this is saying a structure called bad contains an integer, and it contains a structure bad called O. Right, but this structure bad would have to contain an integer and another structure bad, and the compiler will kind of lose its brain over this. So we can't do this, but we can totally do this, right, because this is an integer and this is just a pointer, it's a memory address. The fact that it happens to be pointing to a struct node doesn't cause any problems. But this is the first real data structure we're going to break into in winter term. This is something that builds up what we call a linked list. And it's a really convenient structure for storing and retrieving whatever information, integers, characters, strings, whatever. But once we wrap our heads around this idea, then we can start going a little crazy. And we can start doing things like, okay, I'm going to define a linked list, going to be some kind of structure with some properties to it. And the entries in my linked list, instead of being integers or characters or strings, they're going to be linked lists too. And we'll have a linked list of linked lists. And that's perfectly valid, right? But you need some kind of framework that makes it possible to think about these things abstractly without having to go back to this kind of thing, without having to think about how these things are constructed. So it's going to be a continual process moving towards object-oriented design in Spring. But we're going to be doing low-level stuff in C. We're going to be dealing with ampersands and asterisks and mallocs and all that kind of stuff. But we're moving towards being able to sort of think abstractly in higher and higher terms. Okay, so that's why 224, you really want to pin down the fundamentals of working in C, which you've done, so that we can just start building on top of those. All right, so how much do you know about the malloc statement? Raise your hand if you love malloc. Okay, raise your hand if you know about malloc. Okay, cool. So since we're doing pointers, we can do this. We can say DE is a dictionary entry, but DE is one particular dictionary entry, right? And if we're building a dictionary, we want 1,000 dictionary entries or 1,000,000 or some number. If we want multiple ones, we have to make this an array, right? Struct dict entry DE bracket 1,000. But that limits us to 1,000, and it also uses up 1,000 dictionary entries worth of memory. And it may make more sense to sort of create these variables while the program is running. Now, if we say struct dict entry DE bracket 1,000, it creates space for 1,000 entries when we compile the program, right, or when we link it technically. And when the program starts running, that chunk of memory is already allocated. It's already there. Maybe you only need 10 dictionary entries, or maybe you need 1,000,000, right? So what we're going to do more typically is make DE a pointer to a dictionary entry. And if we need another entry, we'll find memory for this at that moment when our program is running. And so this is where malloc's going to come in. So typically we would say DE equals malloc, and we tell it how many bytes we need. Well, how many bytes do we need for a dictionary entry? Well, we could try to add it up, but don't. We need 201 for a phrase. We need maybe 4, maybe 8 for a count, depending on what kind of computer we're running on, and maybe 4 or 8 for a first. And integers like to be sitting on memory addresses that are divisible by 4 or 8. And if we start off at location 0, and this is 201 characters, the next location in memory would be 202 locations past the start. That's not divisible by 4. So the computer would probably want a couple of bytes of empty space in here. So it may actually allocate 204 plus another 8 is 212, right? So we don't want to have to know those kinds of details. So we use size of, and we tell it what kind of thing we're trying to allocate memory for. So size of struct dictionary entry. And the compiler, which knows how big an integer is and how it likes things to be aligned by multiples of 4 and so on and so forth, will replace this with a number, 212 or whatever the right number is. So we do a malloc on size of whatever our structure is, and that should give us memory.
What if you have a list in your structure or an array or something?
See, if you have an actual list, you don't know how big it is, but if you have a pointer to a list, pointers always have a fixed size. And that's the other reason why we want pointers. That was a short answer, but it's really a deep question. So what does malloc do? Malloc goes off to something called the heap. It's a structure. It's part of the operating system, and it looks for a chunk of memory. So if I say malloc 212 bytes, it will find somewhere in its heap memory a chunk of at least 212 bytes in a row, right? Because if your memory is broken up in pieces, it doesn't do you much good. So look for a continuous block of at least 212 bytes. It will return the address of the first byte as the function's value, and it will do whatever magic it does internally to make sure that nobody else tries to use this chunk of memory. So it'll basically pull it out of the heap and mark it in some way to say this is in use. And now DE points to the beginning of that, so if I say star DE, that's the actual contents of that first byte of the block that malloc gave me. So 121, did you talk about free? So free is how you undo a malloc, because when you malloc, the system has to know this block of memory is in use, right? So that other things don't take advantage of it. Don't try to use the same block. But if you're done with it, and you don't let the system know that you're done with it, that block of memory is still allocated. And if your program never exits, eventually you can run out of memory. So when you're done with a block of memory that you malloc, you go ahead and you say free, you pass it the address of the beginning of that block, and it will undo what malloc did. It'll take it and it'll basically put those locations back in the heap and say, okay, these are available for whoever wants to use them. And so a memory leak is a program where you malloc more than you free. So think Firefox a few years ago, right? It was a notorious memory leaker. The longer it ran, the lower your system memory got. Now, if you exited Firefox completely, your memory came back, and then you could rerun it, and you'd be good for another few days. But it had bugs where things would be allocated with malloc, and most of the stuff would be freed, but somewhere there was stuff being malloc that wasn't being freed. And the longer it runs, the lower your available memory becomes. And memory leaks are a classic, notorious problem with data structures anytime that we're doing dynamic memory, which is 222, but we'll also learn some tools that help us find memory leaks. There's a tool that we'll spend a while playing with called Bowel Grind. And we can Bowel Grind our program, and when we exit, it'll tell us if we had any memory leaks. It'll say you got 2,000 bytes that you allocated and didn't free, right? Or 2,000 bytes that you allocated, but you lost track of them. Your program had no way to get to them when you exited, so you couldn't have freed them. And this is fun stuff. If you like sort of detail-oriented work, you'll totally love.
Would that mean if you're like wanting to use malloc and free, should you treat them kind of like brackets, where it's like every time you malloc, you should also have a matching free somewhere in your program for that? Or?
Effectively, but they don't usually lay out in pairs like that, like
or
brackets
have, like,
do.
Situations where like you try and free a malloc, but the malloc like nested within a bunch of functions, so even though you free it, it might only free like once every.
So you can free something that you're not actually done with, and that can be weird, because then if you try to use it again, it might have changed value. Or you can forget to free things that you malloc. But typically you'll malloc things throughout the life of your program, and it may only be at the very end when you're done that you want to go ahead and free everything. And it may be one loop, whereas you may malloc in 12 different locations. So it can be tricky trying to catch all of those. But Bowel Grind will definitely help us with that, because it will tell us that we have memory leaks, and it will give us some information that will help us pin down where they are. All right, so we'll leave it there for now. Again, this was all just kind of preview of some of the stuff in 222. In 222, we'll start from the beginning with pointers and asterisks and ampersands, and we'll build up very methodically. So go through the study guide on Canvas if you like, and bring questions. Otherwise, we'll just kind of talk through what you can expect on the final.